In concrete structures, we deal with the design of RC elements such as slabs, beams, columns, and footings. Now in this video, we are going to focus only on three design parameters such as design for shear, design for bond, and design for torsion. Now let's get into it. First question is, the chances of diagonal tension cracks in RCC member reduce when? Axial compression and shear forces act simultaneously. Axial tension and shear force act simultaneously. Only shear force act and flexural and shear force act. So what is the correct option regarding the question? That is nothing but the chances of diagonal tension cracks. When it will reduce? What is the criteria? When the axial compression and shear force act simultaneously, then the chances of diagonal tension cracks is reduced. Now let's see how it is reduced, how strength is increased. You can see here, as per class number 40.2.2 of IS 456, there they have given one multiplying factor for shear strength. During shear strength calculation, in case of axial compression and shear force, member subjected to axial compression and shear forces, we have to multiply that shear strength value with this multiplying factor, so that shear strength is increased by this amount. So del is equal to 1 plus 3 pu by Ag FCK. So what is Ag? Gross area of the beam section of the RCC section, and FCK is the characteristic compressive strength of concrete, and Pu is the factored load. So this is the multiplying factor we have to employ, so that shear strength is increased when the RC member is subjected to axial compression and shear forces, and this multiplying factor shall not be more than 1.5 in any case. This formula, that is this multiplying factor, is based on LSM, limit state method, and in case of WSM, working stress method, then the multiplying factor goes here. Del is equal to 1 plus 5p by Ag FCK. So these two formulas are adopted to gain the shear strength in case of member subjected to axial compression and shear forces simultaneously. So here you can see in this diagram. So these are some diagonal cracks, and this member is subjected to axial compression. So in order to gain, or in order to increase the shear strength, we are using multiply this factor, so that diagonal tension cracks reduces, because this member is subjected to axial compression. Now let's move on to second question. As per IS 456, the anchorage value of bend shall be taken as option A 4 times the diameter of bar for each 45-degree bend, option B 6 times for each 60-degree bend, option C 5 for each 45-degree bend, option D 5 for each 60-degree bend. So this is based on the anchorage length of bend, anchorage value of bend. So what is the correct codal provision that is given in IS 456? So the option A, that is 4 times the diameter of bar for each 45-degree bend, is the correct one. Now we shall see more about other values of anchorage length. This is given in class numbers 26.2.2.1. For bend, it shall be maximum of 16 times the diameter of bar, and minimum 4 times the diameter for each 45-degree bend. So here this is the maximum value for bend values. In case of hooks, the anchorage value of a standard U-type hook shall be 16 times the diameter of bar. The third point is the anchorage length of straight bar in compression shall be equal to development length of bars in compression. Development length is given by LD. We shall see more about it in upcoming slides, what is development length and how it is calculated. Now we shall focus only on the anchorage value. Here you can see three diagrams. For 90-degree bend, the anchorage length shall be 8.5. For 135-degree, it shall be 6.5. And for 180-degree, it shall be 4.5. So this is how we have to calculate the anchorage length of a bend. And in case of hooks, it shall be 16.5. So these are the codal provisions given in IS 456-2000. Now let's move on to third question. The RC beam of cross section 420 cross 600 mm is subjected to a shear force of 100 kN and torsional moment of 40 kN/meter. So they have given three values. One is cross section, one is shear force, one is torsional moment. We have to find the design equivalent shear force, that is V suffix E. So we have to find VE. We have to employ only one formula to find design equivalent shear force as per IS 456-2000. They have given a codal provision for this design equivalent shear force formula. We have to employ that formula to find the answer. So here the correct answer for design equivalent shear force is 378.57 kN. Now let's see how it is calculated. This is as per class number 41.3.1. You can refer this also in IS 456. So their equivalent shear force can be found as V is equal to Vu plus 1.6 Tu by B. So what is Vu? Factor shear force. So 1.5 times 100. What is Tu? Factor torsional moment. That is nothing but 1.5 into 40. So 40 is given. So we know the values of Vu, Tu and B also. What is B here? 420 mm. So that just simply substitute all the three values here to get the answer for VE. That is nothing but equivalent shear force. There is another thing called equivalent moment. ME1 is equal to MU plus MT. What is MU? MU is nothing but the ultimate moment of resistance of the RC beam. What is MT value? MT is nothing but equivalent flexural moment, and that is given by using this formula. MT is equal to Tu into 1 plus D by B divided by 1.7. This formula is, can also be found in the class number 41.3. So we know what is Tu. So here they have given us capital D. What is capital D? Capital D is nothing but overall depth of a beam. Overall depth is different from effective depth. Effective depth is given noted using small d. Here we have to apply only capital D, that is overall depth. In this formula they have given us overall depth. We have to apply one. We have to substitute only the overall depth value. So this is the formula to get the answer for MT. If MT value is greater than MU, then we have to find another equivalent moment that is employed for flexural compression phase. Then what about ME1? ME1 is employed for flexural tension phase, that is bottom. So for tension phase, ME1 value shall be adopted, and in case of MT is greater than MU, then ME2 is found by using difference MT minus MU, and that has to be given for flexural compressive phase. So these are some codal provisions and criteria regarding torsional. Now let's move on to fourth question. So before moving to fourth question, you can refer more about torsion and torsional other codal provisions in this video summary of IS 456-2000. Just click here to get more about IS 456 codal provisions. Now let's move on to fourth question. The anchorage length of three bundled bars in contact and of equal diameter in compression is what? So this question is also based on anchorage length. We have already seen one question regarding anchorage length. So here another question regarding anchorage length. Here they have given bundled bars and those bars are in compression. So what is the answer to get the anchorage length of this scenario? So option B, 45 5. 5 is nothing but diameter of bar. So how it is calculated? As per class number 26.2, we get the value of LD. What is LD? Development length. We have already seen a point regarding anchorage length of bars in compression shall be equal to development of bars in compression. So they have mentioned clearly the compression, clearly that the bars are in compression. So that's why anchorage length shall be nothing but the development length. So LD is given here LD is equal to phi into sigma s divided by 4 tau BD. So what is phi, diameter of bar? What is sigma s? Sigma s is nothing but 0.87 Fy. What is Fy? Yield strength of bars. For example, if you use Fe 415 bars, then Fy, that is yield strength of bars or steel reinforcement, shall be 415 Newton per mm squared. So this is how we have to calculate sigma s value. And what is tau BD? Bond strength. And they have given already in the question tau BD value as 1.2 Newton per mm squared. Here they have mentioned as compression. So when bars are in compression, we have to increase tau BD, that is bond strength, by 25%. And if we are using HYSD bars, that is nothing but high yield strength deformed bars, that is Fe 415 or Fe 500 like that. If we use Fe 250, that is mild steel bars, we don't increase anything. So we are assuming that we are using a high yield strength deformed bars, for example Fe 415 or like that. So for that we are increasing tau BD value by 60%. So here we are increasing tau BD value, that is 1.2, as 60% for HYSD and 25% for compression. So this is the actual tau BD value. In this case we have to substitute this value over here so that we can find the answer for LD. So by substituting all those things, we will get the answer for LD as 36.775. Now they have mentioned as 3 bundled bars in contact. They are not using only one bar, they are using a bundled bars. So how many bars are there in a bundle? 3. So for 3 bundled bars, we have to increase development length by 20%. So that's why 1.2 into 36.77 gives the answer as 45.5. So this is how we have to calculate the anchorage length in case of bars in compression. So that is nothing but the development length, simply the development length. In case only 2 bars bundled, then we have to increase the development length by 10%. In case of 4 bundled bars, we have to increase development length by 33%. You can visualize how it is bundled like this. Here 2 bars bundled, here 3 bars, here 4 bars. In case of 4 bars in contact, we have to increase 33% in development length. In case of 3 bars, like here in this question, we are increasing 20% in development length. In case of 2 bars in contact, we have to just increase 10% in development length, that is LD. These are some important things about development length and anchorage length. Now let's move on to 5th question. The ultimate moment of resistance of a simply supported beam is found as 114.2 kilonewton meter. It is having U-type hook at center of support. The factored shear force is given as 150 kilonewton. What is the maximum value of development length? So this question is also based on development length. They have given the values such as ultimate moment of resistance, that is Mu, and factored shear force also they have given. So we have to find the value of maximum value of development length, that is LD. Here some different formula is adopted to find the value of LD. Let's see how it is calculated. Option A, 1309.73 mm. So how it is calculated? As per class number 26.2.3.3, development length shall be given as 1.3 times m1 divided by v plus L0. What is L0 here? L0 is nothing but anchorage length. So here we are adopting the maximum anchorage length. So we have already seen the maximum anchorage length in case of hook, in case of U-type hook, as 16.5. We have already seen in one of the previous questions. So L0 is nothing but 16 times diameter, and here they have given the moment value. So M1 is known. They have also given shear force value. So V is also known. So just substitute the values of M1, V and L0 by using this formula to get the answer for the development length. This is based on class number 26.2.3.3. LD is equal to 1.3 m1 by v plus L naught. L naught is nothing but the anchorage length for hook. For hook, L naught is 16 times the diameter of bar. Here you can visualize what is the development length. In case of support giving compression confined by compressive action, then development length shall not be greater than 1.3 into m1 by v plus L naught. If there is no compressive action, then we are not multiplying that factor 1.3. Just m1 by v plus L naught. That's enough. If the support is not confined by compressive reaction. Here they have not mentioned anything about it. So just simply assume that it is confined by compressive reaction. So that's why 1.3 m1 by v plus L naught. L naught is anchorage length. Here they are using U-type hook, so that's why 16.5. Now let's move on to sixth question. The maximum allowable shear stress depends on which of the following as per IS 456 for design of RC beam. So what is the maximum allowable shear stress? That is so depending on which parameter, maximum allowable shear stress is calculated as per IS 456, whether it is grade of concrete or grade of steel or both the grades or percentage of reinforcement. So here point to be noted is maximum allowable shear stress. So the parameter is grade of concrete. Now let's see more about it. So this is purely as per table number 20. Tau z max, that is maximum or critical shear, is equal to 0.625 root FCK. Actually in table number 20 they have given the values corresponding to the grades of concrete. So that can be given simply by using this formula. Tau z max is equal to 0.625 root FCK. And design shear strength without shear reinforcement is given in table 19, and that is based on percentage of reinforcement and the grade of concrete. See, there is a difference between maximum allowable shear stress and design shear strength. Design shear strength is based on percentage reinforcement and grade of concrete. Here you can see the table number 19. This is the percentage reinforcement value and this is the concrete grade. By using both the values, we have to find the values of design shear strength. So these are design shear strength based on percentage reinforcement and grade of concrete. But in case of maximum allowable shear stress, that is given in table number 20, that is purely based only on grade of concrete, and that can be given by using this formula 0.625 root FCK. So why design shear strength is based on percentage reinforcement? Because tension steel increases the EXIV value, depth of neutral axis, and by increasing that EXIV value we are increasing the depth of uncracked section. So thereby it gives double action and aggregate interlock. So these are the reasons by which design shear strength is proportional to the percentage reinforcement and grade of concrete. Now and we shall see more about other things. As per class number 31.6.3, permissible shear stress is given as Ks tau c. And what is Ks? Ks is given by using this formula 0.5 plus beta c. Beta c is nothing but ratio of shorter side to the larger side of a column. And tau c, that is critical shear stress, is given by 0.25 root FCK in case of limit state method and 0.16 FCK in case of working stress method. So they may ask like ratio of shear stress for LSM and WSM. What is that? 25 by 16. 25 by 16. So 0.25 root FCK and 0.16 root FCK. These are nothing but these are related to the permissible shear stress, and that is given on class number 31.6.3. Now let's move on to 7th question. In flexural members, the maximum shear stress occurs between support and load at the face of the support within 2D distance from the support. What is small d? Effective depth of beam. None of this. So this question is based on the critical section for shear. In flexural members, in members subjected to bending, maximum shear stress occurs where? So what is that section? Nothing but at the face of the support. At the face of the support only maximum shear stress occurs. Now let's see, or now let's visualize using these diagrams. Here you can see where shear force occurs at the face of the support. Here you can see shear force occurs at a distance d from the support in case beam like this, simply supported beam. Here fixed beam, shear force occurs from the distance d from the face of support, and here you can see one thing. If a heavy load or heavy point load is acting within the distance of 2d, then shear force will act at the face of the support. So these are some criteria for critical section for shear. By using this diagram, we can identify what is the critical section. Now let's move on to 8th question. The torsional reinforcement in RCC members, RCC beams should be placed at. So where the torsional reinforcement has to be placed in RCC beams, whether it has to be placed at each corner of the beam, or middle of each face, or middle of beam, or core of beam. So what is the place? Each corner of the beam. So torsional reinforcement in RCC beams shall be placed at each corner of the beam. Here you can see. So at each corner of the beam, torsional reinforcement shall be placed. Torsional longitudinal reinforcement shall be placed as close as practicable to corners. So we have to place torsional reinforcement as practicable or as close as is practicable to the corners of the cross section. In all cases, there shall be at least, when the cross section is greater than 450 mm, additional longitudinal bars shall be provided to satisfy the requirements of minimum reinforcement and spacings. So when the cross section, that is depth of beam, is greater than 450 mm, we have to provide additional longitudinal bars that will satisfy the requirements of minimum reinforcement and spacings. What if when the depth is greater than 750 mm without torsion? Then we have to provide side face reinforcement. So these are some criteria regarding torsional reinforcement. Now let's move on to 9th question. 9th question is based on lap splices and lap length. Lap length of reinforcement in compressions shall not be less than 26 pi, whether it is true or false. So there are some criteria regarding lap length and lap splices. Here they have given for lap length for compression, reinforcement in compression shall not be less than 26 pi. Pi is diameter of bar. Whether this criteria is true or false based on IS 456 codal provisions. This is false because this is not 26 pi, that is 24. Lap length shall not be less than 30 times the diameter of bar in case of flexural reinforcement, and in case of reinforcement in compression it shall be 24 pi, not 26 pi. That's why it is false. So lap length, so this is the lap length, you can see here in this diagram. This lap length shall not be less than 30 times the diameter in case of flexural. In case of compression, it shall not be less than 24 times the diameter of bar. And these lap splices are generally not permitted for very large diameters. For example, diameter of bars is greater than 36 mm. We should not provide lap splices because there will be some breakage of tie. The lap length should not be calculated on the basis of smaller diameter. Should be calculated on the basis of smaller diameter bar, smaller diameter of bar. So if we are splicing two diameters of varying diameter, we have to adopt only the smaller diameter. The design strength of welded splice should be limited to 80% of the design strength of the bar in tension splice. This criteria is based for welded splice. So design strength of welded splice should be limited to 80% of design strength of the bar in tension splice. In case of end bearing splices, these end bearing splices is given for bars in compression. When the bars are in compression, end bearing splices shall be given. So these are the coded provisions regarding lap length of reinforcements. Now let's move on to last question, 10th one. Corrosion causes what? Circumferential tensile stress in concrete. Cracks will be parallel to the corroded reinforcement. Radial tensile stress in concrete. Cracks will be perpendicular to corroded reinforcements. So here two options are correct. This is of MSQ type question. So we have to choose both the correct options. So the correct options are B and C. First option is best for cracks. How the cracks will be? Cracks will be parallel to the corroded reinforcement, and stress will be radial. Radial tensile stress will be there. Radial tensile stress in concrete. Let's see some other points regarding this. Corrosion in steel occupies more volume than volume of reinforcing steel. So that's why it exerts radial pressure. Corrosion in steel occupies more volume. So if suppose here corrosion happens, then that steel will occupy more volume than the reinforcing steel. So that's why radial pressure is exerted on the adjoining concrete layer. So as a result, cracking results along reinforcing bars and concrete starts spalling. Spalling means it gets removed out. So these are the some effects of corrosion. So we are at the end of this video. If you like this video, please like, share, comment and share with your friends. Thank you.